you have a purpose. That's why I have this slogan in my first slide. Learning today, designing tomorrow, and building a strong foundation for career in electrical design engineering. So it didn't start with working today. It didn't start with getting so much money today. It started with learning today. Some of us we are actually all engineers. I graduated from JQuat, and actually my next profile will speak a lot about my introduction. I finished in 2021. I'm not that old into the industry. I'm in my 5th year. And all of us have history. All of us have something to speak about what they have done. Whatever you see on your screens are just definitely what my professional life has been like. I started from just humble beginnings. When I got out from school and like life seemed different because adaptation to the engineering more so electrical and electronics outside here is a stretch. My colleague Ben Okumu and engineer James could agree to that. But it's a point where we need to change. And Roads Up is where we start that. I went to JQuat, did a degree in electrical electronics, 5 years down the line, done, got out. The first institution I went in was Visca. That's when I started learning hands-on skills. That's where I started my whole entire life. After a program with them, I never knew that there was anything more I needed to do. But now something opened. I started a job at Apex Steel. Just a simple, actually my portfolio was electrician. Having done a degree, I was called an electrician. I never took that personal. I just went in and started diving into understanding the systems. Back then, just the simple knowledge I had acquired in the engineering institutions have gone. I then moved out to Apex Steel and went into design. For LG, Can, General, Grain Bulk, those were my attachments. I used to get so much about engineering since I started off my attachments to date that it has impacted positively to me. So one day I started working on AutoCAD Electrical. And that's actually my journey. I started with AutoCAD Electrical. I didn't know anything or any much software, even though we have a lot. So as I was going through, I got an offer at Specialized Power Systems. It's another panel building company. And I started building myself in designing switchboards. We call them switchboards. We call them panels. We call them enclosures. Any central point to where power comes in and our loads can be fed and run properly. Later, my skills were sharpened. I started building myself because I took it personal to study a different software from which we complement drafting in this industry. So I started with AutoCAD, and when I got into panel building, I was forced to learn EPLAN Electric P8. I know for most of us, it's a new software. Some of us, you've heard about it. But again, it's a point of learning, getting to know the different things that will push you from one point to another. So I got another offer within the same environment of panel building to go to Switchgear Limited. All these companies are in Kenya at industrial area. I think most Kenyans will understand industrial area. So I started designing. I got a mentor called Gary Barlow. He took it personal to enable me to sharpen my skills. I didn't take time. Over a period, I was at Switchgear. Every single grind paid a dividend. I started my own design brand, and it's called Dropbox. So I took it very humbly, and I started helping students based on a pro bono, no strings attached. I'm not interested with your money. Just growing and trying to speak to the students and trying to engage with them. Since then to date, I met James, and we had a discussion about inclusion of electrical systems, inclusion of electrical trainings. And to date, we are here. We have this webinar for you to actually see what is in store for you. So that's just the introduction of myself. If you want more, you can visit LinkedIn or any other platforms that people use to share their information. So I'll go directly to today's session. But before I do, I want to actually show you why is it that you need to be part of this. One thing I've known over the years, opportunities in the electrical engineering arena is wide. We have so many categories, but we have what we call misinformation. People are misinformed. I've actually been following your conversation in the two groups Engineer James created. Every single item you send in that group speaks a lot about you as a person. And also for us who are in the capacity of trying to push and actually build capacity of other people, we get so much when you guys communicate. People want jobs. People want to be included in different aspects of engineering field. But we don't understand what are the major categories of these fields that we need to be part of. We know about power generation and utilities, but who cares to know what job opportunity can be gotten from that category? We have industrial and manufacturing, building services and construction, switchgear and control systems, renewable energy sector, telecommunication, oil and gas and mining, transport infrastructure, technical sales and business roles, governments and regulatory bodies. Automatically, if you pick a specialization, if you're a student in this platform, you don't need to rush into starting getting money. You need to rush into converging into what skills you need to acquire for the society in the electrical arena or any field that you're handling to appreciate you. So pick any, identify which one you're good at. Do you want to be protection and controls engineer? Do you want to be an automation engineer? Do you want to be a site electrical engineer? Do you want to be AutoCAD electrical designer? Do you want to be a solar PV design engineer? Do you want to be a fiber optics engineer? Do you want to be high voltage engineer? Do you want to be airport electrical engineer? Do you want to do business development in engineering? Do you want to be an energy officer? All this will bring you into the global employment. And in this case, we are talking that each and every concept that we need to acquire needs to have an end game. You need to be very clear, you as an engineer, what is your end game? Don't just be there to learn. Know what you're learning towards. And today's presentation, based on its structure, you will get to understand the difference between experience and just knowing things. Experience comes by identifying a concept and building it up. Give it time to grow. Engineering is wide. You wouldn't be in every field because it's impossible. You wouldn't learn all the software because it's impossible. Which one do you want? And what are you going to actually utilize you as a person to acquire all the skills necessary? So what are the various high demand skills we have in Kenya? Electrical switchboard design, that's for my country. I know it's the same for the others. Electrical P8, AutoCAD, ETAP, that is power system studies, solar PV design, PLC and SCADA, protection coordination, industrial automation, EV charging infrastructure design, electrical project management. All those are there for you to pick and identify. But the aim here is for you to know, what am I passionate? The word here is passionate. Don't look unto another person and think you can define your life. Everyone has their own opportunity. Pick your path and close the eyes and build your foundation. Start from the lowest point. For the students, you have a lot of time. For those who are practicing and you're still confused, there is always time. I've just told you, life starts at 50. You can actually know how many years you really have to make sure your life pushes. So the reason we want you to be part of RoadSub, it's for these professionals, for these things that will increase your pockets, for these things that will make you make a lot of money, because money is the bottom line. You don't want to have a negative return on investment. If you come to us, you get a skill, and then you get a job. It's a positive thing for us to speak about, because it gives us the chance to proceed with what we're doing and growing the generation to come. So just ask yourself, are you ready to be part of us? Can you be part of us? So that is the basis of my presentation. And today, I want to bring you to the switchboards. Anything that you see, let's say electrically, it means electricity is present. Current passes through, a load is present, we have a source somewhere, and we have machines running. And the economy changes every day. So when you talk about switchboards, people will have different views, because maybe you really don't know what is this, for maybe those who are still growing in this field. But for those who are professionals and maybe the engineers in the market, you really know what switchboards are. But don't you know these things are just built by people? All the engineers that are there in this field, they just sit down and give it time and design systems. So a switchboard is a centralized assembly for distribution. So it's a centralized, we put it somewhere and it can be able to distribute. It can also control, it can protect, it can monitor electrical power. But the point is, it's a combination of items. Before you can be able to actually come up with it, you need to have the design process. That's why I'll introduce you into the design consideration of switchboards. So I tried to expand what was inside that panel. And what you can see, it's actually a changeover control system. The image on the left, it's a discrete component control system that can be able to switch between two sources by controlling a circuit breaker. In this case, I'm talking about air circuit breaker. So we have motorized air circuit breakers that you can set, one for mains, one for generators, and you're supplying in power, and you can use a set of discrete components. Actually, we call them classical controls. You remember, for people who do electronics, we have what we call discrete and controller-based systems. Discrete components is when you can use a capacitor, resistor, inductor to create a circuit in electronics. But when you come to electrical, or what we call power, we can actually combine what we call switch gears together. In this case, we call them control gears, contactors, circuit breakers. This is actually a PLC, okay? And then you have your relays, phase failure, on delay relays. You put them together and then you put them in a switchboard, and it can actually process electricity very well. And this environment, I was very interested to it because all systems globally run on switchboards. I just want you to actually share if you have been around an industry that puts circuit breakers on the wall. Maybe if the country is underdeveloped. But for the developed countries and also those that are developing, we actually have an art, a piece of metal that is purely designed to process power and supply to different loads for it to be able to actually increase the efficiency and how a system will run. So what you see in this image is what we are going to discuss. This is the end product. But what is the process of going about creating it? Because that's what we need to train you on. Or if you're good at it, you need to train another person on it. Because we grow by working together. Engineering is not a solo thing. It's something that we work together for us to achieve the common aim of making the economy automatic and making the economy sustainable. So I'm actually now going into the design considerations. In this case, I'm trying to talk about what really informs for us to come up with a switchboard, a panel, an enclosure. It can be a control panel. It can be a power control center. It can be a motor control center. It can be a power quality center. Either of those systems that you've used in your daily routines. People have maintained them. You go in a power room somewhere in a given factory and you find a lot of switchgear, transformers, ring main units. You get power factor correction banks. You get reactors. Anything that will make sure the load that we connect to these systems run efficiently without delay, without having a decreased efficient in operation. What really informs that? Anytime you're in this trade, you need to obey a client because client information is actually one which will give you the opportunity to come up with a system. If your client is an industrial set, is a commercial set, is a residential set, you need to understand what do they need. What is their supply source? What is their voltage level requirement? What is their frequency? What is their future expansion requirements? So it really brings you very close into coming up with a design because the client will tell you everything they need. You listen to them and you start developing ideas in your mind. Number two, every design that you build, you need to actually make sure the client is comfortable with what skills you have. Because the main objectives we have in creating systems is purely for safety, reliability, maintainability, scalability, efficiency, and compliance. Because if you're not making your system safe, people will die. Engineers will be maimed. We now have different bodies that will regulate us based on what skills or what we need to acquire. In this case, we talk about standards. So the compliance of that system is actually based on regulations. If a system is scalable, it means for the future, you can upgrade it from one form to another. You can actually improve performance. If the system is efficiency, the amount of energy it will use will be very, very good to a point that you're not wasting your money on bills. Reliability is a system that will be there when everything fails, it works properly. So all these objectives govern how switchboards are designed. And maybe you wouldn't know because you're not in this field. But we are actually introducing you to it because it is a point whereby you can learn critical thinking of how systems are actually developed. It's not just all about utilizing systems that other people create. You can come up with your own system, depending with what tools you use. So make sure you actually uphold the objectives a system requires for you to become an efficient and an elaborate design engineer. So why do we actually need these systems? Because if a switchboard is actually responsible to run our loads, what really do we need for us to design them? Now I bring you to the assessments, the load schedules. Like how much energy do you need or how much power? So if you just remove H here, you have kilowatt. That means that's power. Over a period of time, it becomes energy. So how much do you need? That's why we do load assessments. You actually check all the connected loads. But now remember, we have something called demand factor. And it actually brings us very close into these systems because we want a very cost-effective system. So what is your demand load? So we need to include diversity factors if you're designing system from different machines, you're designing system from different types of loads. So we have factors that we include when we do design. I have a case study and we will see that. Future expansion. You know, if you really want people to benefit from what you give, you really need to design your system in a way that if they add any load, the system will sustain whatever output it needs. Phase distribution, you don't want to imbalance your phases. You have red, yellow, blue. Can you make sure the current flowing through those cables can be able to balance? And doing that, you assign a load schedule that will distribute the loads efficiently. People just talk about system in the industries, but they are designed, they are built. People put a lot of time. You find a complete system, it went through a rigorous process to make sure it works perfectly. That machines, those control boards for every industry, if you're in bottling industry, let's say like the Cron systems, how do they work? It's just a point of starting from understanding your loads, knowing the quantity, scheduling them, and then we have assumptions automatically. And then you come up with like a final load design that you can put onto these machines and they will run perfectly. That's why you have companies, they don't have downtimes because they put all this into considerations and they made sure every machine is maintained. Every load change is recorded for future assessment and improvement of the system. So load assessment is one of the design consideration we get when we come to design these switchboards because these are the centralized point to which power will come to and be supplied. You have a main breaker, outgoing breakers, and then you have loads. So it means if you do a proper sizing, you do a proper load scheduling, you will make sure your system does not have an issue. And this is one of the things that corrupt a better system if you do it wrong. So when you come to our trainings, we actually equip you with a lot of details on how to go about, because we have different ways of coming up with load schedules. People represent them differently. We have softwares for that. We have Excel for that. We have so many tools that you can use. So again, find it into your mind to know the reason as to why you're servicing your loads and why the switchboards are connected to supply the loads, and they will work seamlessly without trippings or maybe burning of cables and some sort of problems that we experience. So when you do design, load assessment is prudent. Switch gears and control gear sizing and selection. People build control system, and actually it will be very privileged enough to know that AutoCAD and EPLAN, they are actually the same thing. The approach on how to design is different. Because if you can do load analysis and you can select your components, what is it that is remaining? You need to come up with a design that now shows how these components can be connected together to achieve a performance. So you have a simple motor and you want to know full load current. You get that full load current, but now another constraint comes that you need to know this motor has inrush current. So how do I go about that? Do I increase the size of the breaker, or do I just now do the value of the breaker based on the inrush current? But we have options. You can actually go on different curves of the breaker. We have curve D, curve B, curve C for MCBs, and they will trip with different timings. So if an inrush current will take a short time to happen, it means if you take a breaker that has lower switching than the time that the motor runs when it starts, you will be tripping that motor all the time. So you see, that's a design consideration. So before you select or size any device, you need to be sure this device works on this principle, and this is how I'm going to size it. And we have mathematics for that. People come with different ideas. We have even rule of thumbs that can help us size a contactor. All those devices that are there, you need to have a way to size and select. And that's what we call a switchboard design consideration. It makes you become an engineer that does something different from a point of understanding the system. If you understand the system in your field, because I've actually accepted we have a lot of fields in this electrical arena. Whatever field that you're in, you meet all these constraints. And you need, as an engineer, to find ways to actually build a perfect route towards designing whatever systems you're working on. Cards are just bridges. They are not everything. Every design concept is in your head. Don't actually be fooled if you knew EPLAN, you know how to design. That's a lie. EPLAN, MATLAB, Proteus, all those things are just tools. You need to understand them to use them. Computers, garbage in, garbage out. You do a wrong design, nothing happens because you represented it wrongly. So what is the bottom line? The bottom line is to give time to know how these systems are designed before you can do drafting, because you need to have a process. We design a system, we draft, or we design a system, we do what we call study. We study that system. You now remember ETAP. You talk about crime. You want to talk about PSS, Power System Study Software, PSS SynCal, PSS E. So those softwares will give you the analysis to understand how to combine these systems. And all switch gears that you work, either power, control, or automation, you need to do proper sizing, and you need to actually have a way to select them to suit your design. Something very wonderful about this system is that we have the basic elements of electrical systems, like sources. We talk about cables. We talk about components. So these are the key things you'll find in all standard systems. Cables are communication pathways. When you do design work inside a switchboard or even outside to communicate from one switchboard to another or a switchboard to a load, you need to do a lot of cable sizing and voltage drop. So this one is a concept that we have designed a training on it to enable you to know, how can I do them using calculations? How can I do them using rule of thumbs? Because most of us, if I have a breaker of 200, 100 mm squared cable can be used. Someone will ask, how do you know that? And do you have 100 mm in the market? No. If not, 125, yes. 120 mm squared, yes. You see, if you put a lot of repetition into these things, it just becomes part and parcel of you. You go somewhere, check a system in an industrial line, and you can say, this one will burn after 2 or 3 weeks you hear a case. The cable were bundled in a cable tray, they were heating up, and actually they burnt out. So if you don't have these design concepts in your head, you will end up destroying systems. And that's why it's not a direct thing to be included in the industry. People don't get jobs because your employer does not believe you actually know what you're doing. But if you did, someone will actually listen to you and they will know this guy has the details of what is needed. Every cable has resistance. Over a kilometer, how much voltage do you drop? And how can we take care of that? Just yesterday, I was at Metsec Cable, and I think most of the people were here. Some of them, we were there yesterday. And we saw the process of how to develop cables. They go to an extent of doing a lab. They have a lab to test for high voltage stretch for cables, to test for quality, to test for fire resistivity, all those aspects. Why do people do that? It's not just about using cables. It's about how do you connect it to a system? How do you make sure that if a system runs, is running on cables that can handle the amount of current flowing through? I know engineering is all about math. You can see that we have a lot of math. But if you've gone through your 5 years or your 4 years or your 3 years, depending with whatever category of engineering learning you've gone through, it is a mathematical based curriculum. But now this math is actually built with reason. If I understood this concept, and that's why I grouped it for you to be able to know, this is the load current. This one is the current for length and the number of cables per phase. This is the power factor angle. So if you can actually get the purpose of the formula, you can actually master why I'm calculating a voltage drop percentage to actually compare with the standards. And I'm talking about standards because these are the regulators of all this. And I will tell you for free, you are not inventing anything. All the standards there is, if you've ever read IEC, BS, NEC, NFPA, they actually describe to you how to build systems. So you're not actually coming up with any system uniquely. No engineer is smart. Engineers just put consistency to master the art of building systems. So when you're working with your team, be a person who is receptive to understand the concept. If you're calculating, how do you explain to your friends that this voltage drop might cause this and come to a decision? So all these parameters will give us a proper system. And that's why they are called design consideration. You need to put them into consideration for you to grow. Busbar design. That's another area that when we start on this training, we actually give you, how do you select these things? How do you actually know there is an issue with this bus bars? Temperature rise. How much KEF value, fault withstand capacity, this system can work with? When do you use copper and when do you use aluminum? The types of materials that actually make these systems. You need to be very profound to know. If you want to set up a perfect switchboard, you need to actually design the system in a very critical manner for that system to run in actually the most efficient way. So like whatever image I've used, you have these bus bars and they are supplying these outgoing breakers. What do you think the loads connected to these breakers will have on this bus bar if the bus bar is underrated? So you can either overrate a bus bar or underrate it. But the bottom line is we have design processes for that. What is the reason of taking copper and what is the reason of using aluminum? Another thing, if you're working with sensitive systems, do you need copper or aluminum? So these decisions will actually give you a better design approach that will make you build perfect system. And when you come for these trainings, we actually give you a proper route towards them because I've worked with switchgear. I've actually built over 30,000 switchgears for the 2 companies I've worked for. And when I was doing all that, one thing stood out. If you make a mistake, if you really make a mistake in this switchboard, they will burn up. They actually burn up to ash. They can even destroy multi-billion instructions. So you need to make sure design process is considered. And that's why actually we are coming in with this, because design work, people actually avoid it. And I know it's because it seems to be a lot of work, but it's not if you practice over a period of time. You just need 6 months and you're actually designing perfect systems. One of those months, you come to our programs at RoadSub and we give you all the details of what you need to know. And then the rest 5 months is just practicing and going into different industries for you to build systems. So be aware that it's just a route you need to follow. If you skip that route, you will actually destroy the system and you will be fired. And the reason you get fired is not that you don't know, it's because maybe you don't consider going into the details of something before you can actually call yourself an expert. It takes time. I'm not even there yet. I'm still working towards achieving 10 years plus of experience for actually to say, I'm really good in this and that. Even for those people who've been in school with professors, those people are old. Why do you think they are called professors? They have actually put a lot of work. Some of them get even old. But if you're a student, if you're a technician, if you're a contractor, you have your company, you want to run it, just do it right. It will grow. I know the curve is slow, but if you do it right, you will actually build systems that people will actually just be looking at them and marveling. But it's only the simple concepts, the simple design concepts that will make you to be a very perfect engineer. Protection, design, and calculation. That's another design consideration. People you've heard about lightning arresters, they have a way we design them. So lightning arresters, you have surge protection devices. So all this, if you really want to create a design work around them, you need to make sure that every system that is electrical is purely protected. You don't want to lose infrastructure because you didn't consider a high rise. Maybe you put solar panels, like in this one, they are on top of a roof. And then you didn't use the different methods we have to come up with lightning protection. Rolling sphere methods, all those things that you've learned in school. It means you really don't mind building a system, because the first thing you will actually understand, if you do solar installation on rooftops, you need to do lightning protection. If you have switch gears to actually control those designs, you need this device here. We call it a surge protector device for it to actually ground any disturbances that might make your system to be destroyed. So it's very important for you to know that. Very important to come up with a protection scheme. Generators, transformers. These are actually sources, but a transformer is actually a device that will change voltage profile. It doesn't actually supply. Okay, it can just change levels. I think most engineers have Transformers 101 classes. You know the windings, you know the tap changes, but what you really don't know, this device has its own protection panel. We put protection relays inside a panel to actually protect this item. We have actually RMU, ring main units. Nowadays, they are actually automatic. They are very standard systems that when you actually consider getting into studying them, you get the knowledge that you start from designing to installation. These transformers, they are also tested and commissioned. What are the different testing methods? Can you test the windings, insulation level? And actually, you go into a power systems interview, you get people asking, what are the different types of transformer cooling method? And someone just looks at you because you don't want to know them. You don't give, like, just concentration on it. Because if you're an engineer and you call yourself a maintenance personnel, you actually have a lot of knowledge. You interact with systems. So if a generator maintenance period is due and you're not doing maintenance on that generator, and then you're no different from a surgeon who never went to school. And actually that person wants to go into the table and do surgery on someone. Because you know your systems. You're an electrical engineer. If you know your system automatically, it makes you very strong to know that if this system is due for maintenance, we need to go through this process. We change filters, you clean your radiators, you check your exciters, you actually open any system that will make this machine work properly. So when we talk about generator, it can be actually a source of income for you. How many generator types do we have? Brands, Cummins, Perkins, Hedgehogs. We have, I don't know, Caterpillar. We have,
Lista.
yeah, thank you very much, Chris. We have so many types of generators, but we have less engineers who know much about them. I worked with Can General, actually, and we were doing calibrations for generators. We were using a software called Insight, and we have Empower for mechanical people. So you can actually analyze all the sensors in a generator, and the information actually they carry, you can calibrate them. You know, people do control and instrumentation. These guys have some knowledge on instruments. They know how to calibrate them. They know how to actually use them to get some information. That's the same thing engineers do every day on these generators. And actually, all these systems we are talking about, they actually mimic human body. What is your hand? The brain is your CPU. You have nerves. They actually carry 5-volt signals from one place to another. If you see hot water, you cannot put your hand in it. The same thing. We just put components together and actually build systems that will make us very perfect. So all the time, be a person that can be receptive to understand that if I'm sizing a generator, I need a safety margin. I'm selecting a transformer. We have standard transformer sizes. What are those? Okay. Power system studies. This is another area that we actually train people on. Can you do a load flow analysis? Can you do a short circuit study? What is a short circuit study? Remember, if a system is short circuited, the current actually shoots to very high values. Can your system withstand that? So before you even build a system, you can use specific softwares to actually study how the power system behaves, or even a control system for people who have done motor starting study. So we have different ways of coming up with SLDs, and then we actually analyze them and come up with curves, TCC curves from actually PDF documentation, just describing you what are the results of what you gotten. And then from them, we make decisions. People who have built substations, people who have built actually data centers, you actually know we cannot work without knowing what is the short circuit value of a breaker. Is it a 50 kA, 105 kA? And why do we even consider those? Because if you really don't have a proper current carrying capacity for a system, if a short circuit happens, everything goes to ash. So design consideration when it comes to power system studies is very key, very important. Most engineers need to actually develop a way to make sure they can do better system studies using the different softwares that we have. And I've actually listed them there. When I was in school, I used DigiSilent. I think I've come out here, I've used it up. So we have SKM Power Tools, Easy Power. We have a lot of tools we can actually use for the studies. Ingress protection, IP ratings. What is the first thing you need to know about IPs? Combination of numbers that will give a standard for how systems are connected and how actually we build enclosures. And if you talk about a motor, what is the IP rating of a motor? And why do we have 6 and 5? What do they mean? So I know everyone knows about IPs, but if you actually go deeper into these IPs, they affect switchgear design directly. Someone tells me, I want to build an outdoor unit. We call them feeder pillars. So you have a feeder pillar somewhere. That one, you need to put it outside. When rain comes, it's outside. So what are the design processes for a feeder pillar? You need to know them. It has a plinth of up to 300 mm. It has what we call a canopy. Okay, so when you talk about security lights, like this one's on our highways, they actually have feeder pillars to supply power to them. So it's very important for us to know and grow into this because it gives us the best design approach and how to go about building them. For mechanical guys, you know about gasket. You put a gasket around the door and maybe water droplets will not enter into the systems. Because imagine the board is outside. Automatically, if you're working on IP65, you're protecting against dust and you're protecting against resistance to low pressure jets. So if you have water coming in different directions and it's coming at a given pressure, how can you be able to protect it? And that's the main aim of IP ratings. And those are very key concepts when it comes to design. Another design consideration that I've gone to so many industries and I see people doing their own things is cable tray sizing and selection methods. You know, a proper cable tray does not need to be stacked with cables. But what do you do in your industries? You put cables on top of each other. They heat up every day. They destroy insulation. Systems are affected. But you actually don't even know we have a calculation method to determine cable tray sizing. So all the time, remember, when you're building a system, it's more on how you design that than how you build it. Because the design process will give you a proper functionality. And you can also go and test it because we have power system studies. For this, you actually just need to have what size of cable tray do I need? How am I going to arrange these cable trays? So you have two cables and then the distance between them is actually the diameter. But the distance offset from the flange is the distance of the diameter divided by 2. So those are actually just methods we use to make sure we can map our cables properly. You need 20% extra for future. But do you see what is done in our industry? People put cables. This is actually the right way to lay cables. You have like a spare space where in future, in case you have something to run, can actually find space. You don't put another one on top of the other. So on the trainings we offer, cable tray sizing methods are very good. And actually, Engineer James says he's working on coming up with a workshop where we can just be going there and trying to do these things on hand-on. Culminate all the design principles and then go to like now the physical development of things and do it right. Let's say for me to give you a certificate in cable tray. I give you a cable tray, I give you cables. You show me how it's done, you actually pass the test. I don't need to depend on your theories in your CVs. I want to see you doing it. And that's what we are actually going for. We are not interested in knowing what you've done over the years because so many people have done so many things over the years. You're not like the one who was done alone. But what differentiates us is that skill to do about something that will make you actually be better. Earthing system design. Earthing system design. I don't know actually what to say, but this is one of the most fucked up, sorry for that word, things that I've seen in the industry. People don't even care about earthing systems. But let me tell you, a half of how an industry operates is dependent on an earthing system. If you actually have systems that are sensitive to earth cable, you will be very careful on which type of earthing systems you do. Is it a TT? Is it a TNC? Is it a TNCS? Is it a TI? So the different methods and how they are connected. What is the sizing? How do you calculate the value of cable that you need to use for earthing? Because remember, fault current flows through the earth. If you don't size the cable very well, you will actually create a problem. So it's very important for you to know the different earthing methods and actually what we do earthing for, because it has a purpose. Why do we even earth a system? For protection and all that. Okay?
Unaamuka naweka bluetooth.
Evans Murimi, you can mute yourself. So let's talk about data sheets and how are they important. If you can be able to interpret LV switchgear data sheets, you're actually starting developing your design skills, sharpening them. You talk about designing in AutoCAD. You want to draw something in AutoCAD. But remember, that is drafting. That's not designing. So if you really know what breaker size you're using and which type of breaker you're using, all the data are actually provided in the nameplates we have on our devices. We also have technical data sheets like on the internet for a specific manufacturer that you're working with, and they give us a lot of information. So most of the time, be very careful to know how you go about handling your data set. Safety and standards, I wouldn't talk more, because if you really know how much there is for these standards to build a system, it's quite a lot, and it gives us every single rules and regulations on how to work on transformers, on how to work on medium voltage system, low voltage system, transmission lines. If you actually want to become a best engineer, read various standards based on your skill or based on your job. Power quality improvement. Look at the image I've actually used on my right. You have a very distorted power, you're taking it through a system, and you get a very pure sine wave. That's actually making sure your system is better in quality. So sometimes, if you really want to know what affects your system, you need to identify load classifications. Are they linear loads? Are they non-linear loads? What are the harmonic assessment? How does your system actually behave, or what is that system that is causing a lot of harmonics? Like variable frequency drives. You need to put maybe detuned reactors in power factor correction. So voltage regulation, we use voltage regulations systems, AVR, AVS, automatic voltage regulators, and automatic voltage stabilizers for us to make sure that our systems are working perfectly. So power quality improvement design is one of the considerations we factor in. That's why we have actually what we call PQC, power quality centers. We build boards like those to make sure our systems work better. So whatever I've just shared with you in a nutshell is what we call design consideration when you're building these systems. So what are these types of switchboards that we are really talking about? And you've seen these things. Some people, you look at them and you fear them. I'm actually telling you it's like A, B, C, D to design these things. Straightforward. As long as you just design simple concept, and people make a lot of money. If you start your control panel workshop just at home, and then you go take some jobs from people, maybe you build these pump systems for buildings. You can actually be designing them, and then you build them, and then you get money. That could be maybe a hassle for you. And then when you go to the industry, you also grow on different modes of control system. So it's very important for you to actually develop a better way of increasing your capacity. And RoadSub is a place you can actually start from to build that. So types of switch gears: power quality, power control centers, power quality centers, motor control centers, automatic and control centers. This, like when you're talking about PLCs, IO panels, relay timers, communication, all put in one switch gear. So when you're talking about this type, you need to know how to design them and then draft them. So in the industry, there are so many. You've heard about synchronization panel, generator of loading panel. There are so many. Actually, if I try to break them into their various types based on the industries, I can have like a list of 100 units here. We have PLC panels, variable frequency drives panels. We have soft stator panels. We have borehole control panels. So there are so many. But now the bottom line is we give you the fundamentals to start off, to try even understand them. Because if you build these circuits, you actually become very powerful. I've trained most of my friends, and I know some of them are here. And you actually see where things are coming from. For you to actually build a system, you need to design them. You need to draft them. You need to actually take through verification. So the entire project management cycle that you need is based on design, getting the right information from the client and building up a system. So all these types of switchgears are used. But now the bottom line or the question is, do you know how to design them? Can you be able to draft them on AutoCAD? Can you be able to use EPLAN to draft them? Like in just a short session, I'll be showing you like a case study, and I'll go very fast because I can see my time is really flying and we really want to get your questions. So every time go through your industries and identify which panel is this. Can I be able to know what components are inside? Can I be able to design an HMI that is using maybe blah, blah, blah to run a system? So it's very diverse. Now, and actually, I'm actually done with the types of switchgears, and I have a case study for you guys. So assume you have a residential building, electrically, you want to design it. So someone tells you, this is the building, and actually I just gave that image as a sample. You have to come up with transformer size. You need to develop you need to develop a main distribution board, a sub-mains distribution board, and a distribution board, and size all the cables. How do you go about them? So you call yourself MEP, and I don't know what that means. Maybe it's mechanical, electrical, plumbing, but for me, it doesn't matter because being an MEP, it means you just need to concentrate on your field. That's E. So if you're an electrical engineer, what can you do that will enable this building to come to completion? So it's very important that if this system is to be built, you need to have a process. And I'll be taking you through the process. So allow me shift my slides a little. So I'm going to a case study project. You have to come up with an electrical design estimate and drafting for an high-rise building. So try to imagine if it's a residential space, what are the different loads that we have? So the first thing we start from is how do you understand the system? You know, now the building is your system and you want actually to come up with the mappings. So let's talk about a 6-floor building, including ground. So it's 5 floors, including ground. And each floor, let's say starting from first floor, you have 3 bedrooms and 2 bedrooms. And you as an engineer actually needs to come up with this project from the start to completion, meaning you design and then you come up with draft documents that we can use for us to be able to make decisions on how to do maintenance on that system. So the second thing will be, do you really know like the power flow of that system? You're an MEP engineer. Do you know the symbols for a transformer? Do you know what is like a main distribution board for that system? What is the sub-mains distribution board? What are the different distribution boards that you're going to be supplying for you to actually make sure the entire flow receives power? So you need to know the symbols. And the key things about cards is you need to know how to interpret IEC symbols or whatever standard you're using, because we are represented from other countries. So if you're using NEC or you're using NFPA, what is your symbol for a transformer? For IEC, just two rings having an intersection. You have MDBs, SMDBs, and DBs. So you need to know what are the representation so that if you're interpreting that circuit, it becomes very clearly understood, and everyone that works on it has a standard way of understanding your design and your thought process. Now, you need to calculate. And I've actually told you we have a lot of math. I won't go into the details. The slides will be shared. So if you want to come up with an estimate for the 3 bedrooms, because we've said we have 3 bedrooms and we have 2 bedrooms, three units each. So it means you need to understand what is the load that you're working with. What are the sample loads that you expect? Do you know them? Are you actually assuming? Because we also have assumption. And we said if that's the case, it means you get the total amount of power and then you get the demand power. So remember, you have now your total load. You've added up all the loads that you have. And then you include a demand factor. Why is it very important for you to include a demand factor? Because you really don't want to incur costs for that specific load, and all the loads will not be activated at the same time. So when you're being trained on doing load estimation and coming up with load schedules, demand load is one of the details in a load schedule. So for each device, if you do a total based on maybe the environment, if the environment is the same, automatically we can use a single demand factor. But for the industry, for people who have designed industry systems, each system comes with its own demand factor value. So for the 3 bedrooms, we have a demand load of 10.5. For the 2 bedroom, we have a 4.9. I want to give you a secret. For people who do building management services, anytime you get a value of 10.5 kilowatt, compare it to 7. Is it greater than 7 or less than 7? If it's greater than 7, then you can use a 3-phase DB on that system. So the demand factor value, based on Hassan's question, you get it on your standards. Because if you want to calculate yourself based on the environment that you're in, you can actually do that because it's just an equation. Demand factor is equals to maximum load over the connected loads. But now that one, you need to have specific loads. But sometimes if you go into your BS standards for the building codes or the building standards we use for electrical, you will get all the demand factors for different loads inside there. So if you have like this one, if it's a domestic residential, we do 0.7. So we have 3 bedrooms load and 2 bedrooms load. So I was actually telling you, for me to actually develop a system for this load, I'll do a 3-phase system. Why? I have a demand load of 10.5. That's greater than 7. For this other one, I'll do a single-phase system. In this case, I'm talking about dBs because that's the next slide. So you have a demand of 4.9. That's even less than 5. You cannot build a 3-phase dB there because we have different types of dBs. We have 3-phase dBs and we have single-phase dBs, which are called consumer units. Single-phase dBs, consumer units. 3-phase dBs, the dBs you know now. So once you get the demand load estimation, you will actually have a value. So the total amount of 2 BHKs that you have per flow is 3. So 3 times 4.9, you get 4.7. And then you have 3 bedrooms, 3 of them. So times 10.5, you get 31.5. So add these 2, you actually get total load per flow. But now, let me tell you, people have different design process based on standards. I've actually seen standards that do values based on mm squared per something, actually kVA per mm squared. And that is a specific standard that they use. So it means if you know your building and you can actually come up with an estimate table, you can also design for specific loads. But in our country, we actually do what we call load analysis, which is Kenya actually. We do load analysis, get the total loads, and then get your demand load, and then add them. So once I add, I get 46.2 is the amount of power each flow is required to have. And that's an assumption. But remember, we have safety margin over a period of time as you do your design. So in this case, I have each flow with 46.2, 46.2, 46.2. And that I've told you, when you come up with designs, we have assumption. And those assumptions over a period of time, they will be corrected based on the safety margins we include. But now remember, that is for the residential load on the houses that are there. What about common utilities or common services? So let's say you have a lift, you have water pumps, you have lights. So let's say this one just given an example to actually reduce the calculations and maybe a lot of details. Let's say you have a 50 kilowatt for your common utilities. So you will actually use a demand factor of 0.8. And now remember, the one for domestic houses, you have 0.7. For utilities, common services, actually we have industrial-like systems, we go to a different value of demand factor. So you multiply 50 by 0.8, you get 40. Now there, you can actually know the total amount of energy in the entire building by actually adding the flow values. And how many flows do we have? 6. How much power per flow? 46.2. Total demand for the entire building will be summation of demand load for the utility plus total demand load for your houses. You get a 317.2 kilowatt. You can actually follow on the math at a later time to prove yourself. But the point here is when I'm doing load estimation, I use demand load. The reason is you actually don't want to put a lot of expenses when the diversity factor explains to us that each load will not peak at the same time. Each load will not be connected at all the time. Sometimes you're even out of your houses and the load is at 0. So you wouldn't go with the exact load size without putting a demand factor because you will incur a lot of cost buying your items because the sizings will not be realistic. So for MEP engineers who actually do a high-rise building, you understand that because this is what you do every day. Okay? But towards the end, you'll see now what will be the difference for us introducing this. Now, what is your transformer size? So you actually know transformer as a unit that is rated with kVA value. So for you to change the kilowatt demand power to kVA, you need a power factor. And you really don't need to calculate that because this power factor is given on the transformer data sheet or even the nameplate. So you just convert that to apparent power. But now remember, that transformer needs to have a safety margin of up to 20%. Actually, it's 20 to 30. We can do a 25, we can do a 20. We can also do a 30, but it's dependent on your case. If it's an industrial setup, we do 30%. And also, this is dependent on which standard you use, because all of these systems have a way we follow on standards to guide us. So if you do a 20% on 396.5, you have 475. But can you get 475 in the market? No. What is the nearest? And actually, if you go into your net, you'll get all the standard transformer values that we have. I just didn't want to include here, but we have standard values starting from 100 kVA towards 1,000 or 1 MVA value. Okay. So it depends with your exposure because these systems are very sensitive. We do this design to actually make them work efficiently. Now, you've done load estimation, you've done transformer sizing, and you need to know what is your dB sizing for each room. So we've said we have 2 bedrooms. Kelvin, you can unmute Irungu. So we have actually 2 bedrooms and 3 bedrooms. So I was telling you for the 2 bedrooms, you need to get the breaker that is required for the incomer. You know, distribution boards, everyone knows dBs. And I've also told you, since this is a load that is below 5 kilowatt, you cannot actually use a three-phase dB. You will use a single-phase dB. And that's just a rule of thumb. I've actually associated it with my job. That if you have a value less than 7, that system is actually less. Sometimes if it goes below 5, it's even less. So you cannot waste coming up with a three-phase dB for that building. Because what is the aim here? You have this 3 BHKs. So you need inside here a dB to supply the loads inside for the 2 BHK. So I'm saying for the 2 BHKs, you need to design a dB. So I've started from dBs first, which I used in each of these houses, and then I'll go to SMDB for each floor. So you have 2 BHKs and 3 BHKs. So when you're calculating your distribution board, you need to consider getting the total amount of power for that specific, and it's for demand load. And then you need to calculate your current, because we need to start with the main incomer and then we cite the outgoings, because outgoings can be supplying the different loads we've talked about. So you get now this formula. For single phase, coming up with a current value, you have actually two methods. For people who we study with, we use just normal conversion tables online. But just a simple formula, power in kilowatt, you multiply by rated voltage plus power times power factor. So already design power factor estimations are there. And that's why we said when you're doing design, we have assumptions. So those assumptions need to be stated. Like this power factor is an assumed power factor. And we do that because realistically speaking, you wouldn't get a system that is more efficient, even in a building. Because we have motors, we have lifts, and we have pumps, and we have all those systems that have reactive component. So we have a 0.8 for a design. But again, for you to get the main breaker value, you need to do a safety margin. 25%. Actually, that's an average of 20 to 30 in between. So you do that extra value, you get 33.28. So the main incoming breaker, you can actually go to a 40 amps SPN MCB. So it depends with your market. Do you have that in the market? But don't actually shoot to a higher value, because 33.28 is not in the market. Which one is the nearest? So you go to the nearest breaker. So the same math that I've done here, you can now use that math to actually select your system. So I didn't go into a lot of maybe sizing the outgoing loads, but let's say you have 3 lighting systems, you have sockets for the different devices you have. You have geyser maybe in your bathroom and all that. You have kitchen appliances. So if you have number of breakers you need to apply, you need to know how many breakers you have for the lighting, sockets, and other devices. So if you have 3, 3, 1, 1, so the total outgoing MCBs, you can actually add them. So you have 3 plus 3 plus 1 plus 1, you get 8. So for you to come up and say, I need to use a 10-way SPN DB, we do a spare. So you do 8 plus 2, you get 10, because the 2 is a spare. And for people who've seen consumer units, they actually look like the sample I've actually drawn there. So you need to know, this is my incomer, and I'm using a single phase system. So the incomer has a double pole, L and N. And then we have outgoings, and then you'll have your neutral, you'll have your earth bar and all those things. But here you're just selecting, deciding which dB am I going to use for my 2 bedrooms. Same process, you do it for your 3 bedroom. So 3 bedroom, we have 10.5. That's greater than 7. So we go for a 3-phase dB. The same math, the difference is you have a root 3 here. Same math, but you have a root 3. So you do the math, and then just remember, your power is in kilowatt, and your 3-phase voltage is 415. That's the difference now, because the other one was a single phase. And then assumed power factor will be 0.8. and then the three-phase constant needs to be included. But safety margin still sticks. So you need a 1.25 extra. That is 25% extra. So you get 22.82, and that's not in the market, which depending with the range that is in the market, some of them we can get at 25 amps if there is, but you can work with 32. Okay. So you need a 32 amp TPN MCB, but this other one, you needed a 4 amp SPN MCB. So these are specific breakers that will be supplied by the SMDBs, because these are actually DBs that are very close to your loads. So if that's the case, you need now to come up with a sample DB for your three-phase. So remember, you need to have an outgoing breakers for the same. But now the trick here, when you add all the breakers that you have for each circuit, if you get 15, a three-phase DB has a factor of 3 because we are supplying with three-phase. So divide 15 by 3, you get 5. You do a spare of 1, you can go for 6-way TPN DB because that's standard in the market. You see now the difference. Here, I need to divide by 3. Why? Because I have 3 phases. So if I'm tapping single phases from each phases, I need to know how many 3-phase circuits I have. So I have 5 3-phase circuits, but I have 15 single pole breakers that I'm using in that DB. So automatically, what is your DB that you're going to buy in the market? It will be a 6-way TPN DB. The other one, we didn't do a factor of 3 because that was a single pole, just red phase and neutral. So you just maintain the same line because all of them are being supplied from a single phase. But for a 3-phase, we are supplying from 3 different cables. So you need to be very careful when you're doing DBs for 3-phase, because if you don't divide by 3, you will go buy a wrong thing. So now this design, I haven't even started drafting these things. And that's the aim. You now come to cards, the different cards we have, and then you can come up with your design because you've actually developed a proper sizing protocol that will make sure that this process makes you a very perfect engineer. Now, you want to come up with an SMDB. This is a submain. If you remember from my presentation, let me just go back here. We have actually designed the DBs, the 3 ones going for 2 BHK and another 3 going for 3 BHK. But now we are here. We have a panel here and it's a switchboard. Even these ones are switchboards. So this is a switchboard that is supplying this simple board. We need to design per flow. So if I go now into the calculation of SMDB, simple. You need to know each flow was utilizing how much power. So you have 46.2 kilowatt per flow. And actually that's what we got here. 46.2 for each flow. So you need to design as an SMDB for this flow, because remember you have first and fifth. They're actually far away from each other. You don't need a breaker at first, a switchboard at first flow to supply fifth flow. It's not even practical. So each flow will have its own switch SMDB. So how do I go about the design? You calculate your current. So the same formula I've talked about. If it's a 3-phase system, automatically it needs to be a 3-phase system because you're supplying the entire flow. So you have your current, but you're using 46.2. Just remember, it is per flow. So to get the main incomer, you do the current value, that's 80.4. Do a safety margin, that's 100.5. The nearest you'll go for is a 125. You see now, that design, people can do without mathematics. As long as you know how much current you need, you can actually just say, I need a 125. But you need to have a report written for you to actually show the design processes. So the outgoing MCCBs for actually 3 BHK and 2 BHKs, we've actually seen them from the design we've done previously. We had 32 amps and 40 amps. So 40 amps was for the single phase 2 BHKs. And then 32 amps was for the 3-phase DB for the 3 BHKs. So if you're building an SMDB, look at this image on my right. You have an SMDB that is going to supply each flat using what we call distribution board. So we've said for this 2 BHKs, we are actually supplying using single phase DBs. But for the 3 BHKs, we are using three-phase DB. Reason being the power utilization for each flat are different. And this one is per flow. This is for flow 1. We need to do that for all the flows. Because now that's the beauty of MEP. You just do for one flow and you try to check if the other flow is similar to the other one, you can actually do the design. But for commercial building, that is not advised because you can have flow 1 doing different things from flow 2. So you'll need to design for flow 1 differently, flow 2 differently, 3 going up until you can finish. So if you really now know that this is the value 125 that you need for each SMDB, now it's easier for you to now select one. So we said we have 32 amps, 32 amps, 32 amps going for the 3 BHKs. And then now we have 40 amps, 40 amps. And this one was single phase system. This one's were three-phase system. So for this representation, we said we have selected an SMDB, which is a sub-mains distribution board that is going to supply a TPN DB on 3 BHK. I didn't include for 2 BHK because now you will tap from 32, you go to the first. This is per flow. So you need 6 SMDBs. But now the question is, those 6 SMDBs, where are they getting power? They are getting power from a main distribution board. That's another switchboard. Now that one is the final de la creme that is going to supply the entire system, and it's getting power from the transformer and your mains utility. So you need to design for that again. But now before you do that, what is the sizing for your common utilities? You need also a breaker for the common utility. Okay, so it's just a process of iteration. Again, you know how much demand load you needed for the utilities, 40 kilowatt. So that 40 kilowatt, you get the current, you do a safety margin, and then from there, Trevor Petty, please, you can mute. So once you do that design, it now makes you very easily determine the breaker. Trevor Petty, do you have any question?
Nilipelekea yule kijana alikuwa niwekege ile software ya kudesign.
Trevor.
Nikakaa.
So once you do the sizing for your common utilities, you determine.
Nilipelekea hapo 6:30, nikadhani nitamaliza by 7:30 hivi.
Trevor, you're disrupting the session. Can you just mute or leave? Trevor.
So sorry for that. Sorry for that. So when you need to design the entire system, you also need to figure out your common utilities. They need a breaker. So from the main distribution board, you will have actually 7 breakers coming out. 6 going to ground up to the 6th. And then you have the main breaker that will be supplying those. So if you go to the next slide, I've actually shifted now to the cable sizing. Remember, you see this cable coming from SMDBs going to the houses. You need to know how much cable size do you need. That's when now you go through the cable sizing method. Cable sizing method is simple. You just need to know how much current is the system or the breaker that you're supplying has. So all the SMDBs, they have actually a 125, and we selected here. You can see the main breaker, it's a 125. So the cable that is connecting from here going to the main DBs is supposed to be rated based on 125. So when you're doing cable rating, remember we have what we call derating factors. So a division by derating factors, you'll be taking care of the cable laying conditions, temperature. You're also taking care of like it's passing through the underground. We have issues there. So you put a derating factors, the current goes higher. Demand factor, we multiply. Derating factor, we divide it. So you have a 156 after you consider the rating factor. And then from there, you need to go to your tables, because every
Excuse me.
catalog table will actually help you to come up with appropriate cable size. So
I'm sorry.
before you can select,
I have a
I have
question, please.
this cable size table. So if you're working with 156, remember, if you go to this cable size, I don't see any current that is going to be laid on a duct with 156. So I have 145, but we cannot go lower. So I go for 180. So when I check the cable for 180, it's a 70 mm squared. Okay, but we also train you on rule of thumbs. So once you get that 70 mm squared cable, it's actually now whatever you've selected, depending with the current that is derated. So you have a 4-core 70 mm copper XLP cable, and this is how it looks like. But now the question you need to ask yourself, how much voltage drop does that cable has? So we use now the voltage drop formula. And I've actually developed these slides. You can actually understand everything very well. So you know your maximum allowable voltage that you need. Most distribution systems, if the value of voltage is above, the voltage drop is above 3%, we have an issue. So if it's a three-phase system, you have 3% of 415, you get 12.45. So every test needs to have a value below 12.45 for it to actually. So if you do the math, this is √3 current cable resistance length. So where do you get cable resistance? You have it here at 90 degrees. Always take the highest current, the highest environmental temperature that you have. So you go under 70, and then you get a 0.3440 resistance value. And then you come include that value into your cable sizing. So you put your resistance per kilometer. So it means your length. So I'm working with a 50-meter long. So let's say from my SMDB to my MDB, maybe in the 5th floor, the distance that the cable is traveling is 50 meters. So you change that 50 meters to actually kilometers, you get 0.05. So you're just feeding into this formula to get how much voltage drops. We have so many formulas considering different parameters. This is just one of them. If you have now very sensitive buildings, we go into including reactance. That is R value and X value. So it depends. We have residential formula voltage drop, we have commercial, and we have also for domestic. So once you do that, you now get a value that you can compare with the minimum allowable voltage. And if it's below 12.45, it is acceptable. So you've done a rating of the cable, you've tested the voltage drop, you now pick whatever value of cable, because that will be precise if it passes the voltage drop case. But if it doesn't, you go to another manufacturer, because now that manufacturer will not work for you. And this resistance, actually, I told you yesterday I was at MedSec. They are tested. They have resistance table. Those tables are very prudent enough so that we know per kilometer how much voltage can I drop if I'm laying this.
Excuse me.
Okay. So just use your cable catalogs and the formula. Simple for cable sizing. And then you need to now come up with your MDB, which is the final thing. So MDB sizing for the building. You've sized your SMDBs, and I've told you SMDBs now, they have 125. But now, if you want to design for all the 7, because we have 6 floors plus common services. Common services, we've had 100 in the DB that is going to supply the common services. But now, when you come to MDB, we don't give those systems the actual value. We actually go a higher range. And now remember, if you are in the DBs, we are using MCBs. MCBs, they actually have what we call less KA value. They actually trip very fast. So when you're working with high power, you now need systems that can actually handle a lot of KA value. And from our selection here, I forgot to tell you, here we are using MCCBs, but in the DBs, we are using MCBs. So MCCBs, they have the highest KA value because they are handling a lot of power. When you talk about dBs, they have up to 10 KA, and you can actually read on your breakers. They are written there. This is the amount of fault current they can handle. So we have a way to do this. You can do the system study, power system study to get the fault level, or you can actually go with the rule of thumbs that we use to select them. So remember here we are using MCBs. Here we are using MCCBs. Now we are designing for the distribution board. We need to calculate all the 7 outgoing. How much amount of transformer did we calculate? You remember we selected a transformer here and we selected a 500 kVA. Now you use this because we had put a safety margin. So the incoming breaker that will be supplied by the transformer, you need to go again into the 3-phase current formula, do a 20%, and then you select your main breaker. So ask yourself your question, why am I picking SCB? Because SCB has the highest KA value. Even the construction, if you look at it, it can be able to handle more fault current. So if the entire flow is being supplied by this breaker, automatically it will handle, because we've actually precisely calculated the nearest standard SCB we have from 662 amps. So 662 amps is actually a safety margin value, but it's not in the market. So we select a standard 800 amps. So the outgoing MCCB for all the 6 flats was actually 125. But now I'll use 150. And I've told you, the reason I go a higher value is because I'm going into a system that now handles a lot of current. And now maybe you want a specific KA. And these KA values, when it comes to sensitive projects, they actually assess them. If you're building data centers, you really need to know your KA value. You can actually do a power system study for that, for sensitive system. But for domestic, you can actually just pick a breaker that has a higher value than the one inside the sub-distribution boards. You remember sub-dB had 125, but MDB, and sometimes people use isolators in the sub-distribution boards because they know they have a tripping unit or a tripping breaker inside the main distribution board. So when you see those design permutations, it means if you don't put your brain into it, you might design a wrong system. So what is the sample connection we are looking at for? So you have your SMDB, you have your main DB. So how many SMDBs do you have? You have 6 plus the commons. You see now for common services, we talked of 100. Actually, the actual common services value we got was 100. If I'm not wrong, we had 100 TP here. So this 100 TP, when it comes to the main DB where we are getting the power, we put a 125 because the KA value will shoot a little, because now on the main DB, the systems are carrying all the weight of all the DBs for 2 BHKs and 3 BHKs. And we have calculated the total main breaker that we need. And then you need to also do the cable sizing from the SMDB to the MDB size. You need to do the size of those cable. And that's exactly what we did here. And we got that we need a focal 70 squared mm copper XLPE because we used a 125. So you see this 125, we divided by the derating factor, and then we went into the table, and then we got the cable size, we tested for voltage drop, and then we selected that cable. That's the actual process. That's the correct process for you to be able to actually do that selection. And then you do the cable sizing for the transformer. And this one, I just want you to be sensitive because it's the last slide. So when you actually look at this cable sizing for transformers, you're now getting the transformer cable from the transformer to the main DB. We have an SCB of 800 amps. So you have a transformer that can handle up to 500 kVA. You do the full load current for that transformer, you get 696. But you need to include a derating factor. The same way we've done the calculation for the cable between SMDB and SMDBs and the DBs in the house. And then you get what we call a continuous current rating of the cable. So you have 696, but you divide by 0.8, that goes to 870 amps. For you to get a cable that can handle 870 for this cable catalog, it's not possible, because look at the highest current if I'm laying the cable in the underground, because now from the transformer to the main DB, we can lay cables from underground. So I want you to check the last digit. We have 300 mm squared. 300 mm squared, the current inside when you lay the cable in the ground is 490. If you check very well, I don't want to put my cursor there because there is an obstruction. So you have 490 here. So when you come into your math, you have 490, but it's a 300 squared copper XLPE. What can you do for you to carry 870? You need to parallel the cables. You take two cables in parallel. So you have a distance of 100 meters to the MDB, main distribution board, and you have two 300 squared copper XLPE. People will go for 630. Some people will go for 630, but you need to check on your cost and also what cable design you want. So once you now know you're going for 2-core, so it's 2 times 4-core, 300 squared mm, copper XLP. It will be able to carry 490 times 2. That is 980. So this is actually more current. This one is 870. This one is 980. It means that's okay. Future expansion, we also did a safety margin. So the system works properly. But now when you do voltage drop check, you find that it has a 4.88 volt, which is less than 12.45, which is the minimum voltage drop level we need. Just 3% of 415. If that value is below this, it means that cable is correctly selected for that job. So we have 2 runs of 4-core 300 squared mm copper XLP rated at 980. That's the amount of current it can carry because it's twice 490. So that's a selection criteria based on a sizing mathematical process using the formulas that we get on our standards that are there. All these formulas you can get online, you can get on your standards, they're all there. But the point is you need to know how to use them. So once you've done that calculation, automatically you can come up with what we call a power reticulation. Power reticulation design will now give you now the art of going into the cards. Because I actually told you, you don't just go into the cards without doing design. That will be wrong. You'll be just wasting your time. If you can do a proper design and then now you have what can actually be drawn using AutoCAD or EPLAN, you now have a reason to start this drawing. Because you cannot tell me that I want to know AutoCAD and you cannot even come up with a system from scratch. Because what I've just done, people use that to get their licenses out here. You ask few questions about how do you size the entire system supply, and then you get appropriate values. And then you get a class B, you get a class C1, you get a class C2. So if you have that building system architecture, and this is a block diagram SLD, you can actually see now I have the main distribution board supplying the 7 outgoing, starting from the common mains, ground floor, first floor, second floor, third floor, fourth floor, and the fifth floor. And then each of them is gonna outgoing 3 BHKs, and then you have 3 for 2 BHKs. You have 3 for 2, but remember now for common, you have motors, lifts, okay? You have pumps, and then maybe a spare for common. But for ground floor, you have 3 for 2 BHKs, and then you have 3 for 3 BHKs. So this is what we call a power reticulation. Any contractor, any consultant, any person who goes out to get data, this is the final documentation that goes to a draughtsman. And who is a draughtsman? A person who develops technical design. So don't lie to yourself that knowing AutoCAD, knowing EPLAN is all about you just being taught on how to draw them. At RoadSub, we don't do just softwares. We make sure that the system is understood. How do I now rate the system? How do I select the cables? How do I select the components? And then from there, we go worry about drafting. So the question is, which of these two are you familiar with? Because for me, I even don't care about EPLAN. I'm very proficient in it, but I don't care. If I don't know how to design, then I won't know how to draw. And this is just a residential case. What if you're given a data center? What if you're given a substation? What if you're given for like to design for a school, a university, let's say like Moi University, JK Watt, KU, UON, you need to design the entire system of how all loads in each and every rooms, offices, kitchen, and how they are going to be supplied with power. And then for you to now go to a draftsman to develop for you switchboards, you need to come up with a power reticulation. Something that from the transformer, we have cable sizes. We've used a 2-run 4-core 300 square. And then from the main DB going to the sub-distribution, we've used a 4-core 70. I didn't do the calculation for this, but you can do them for the specific DBs. You can do how much cable you need. So that from there, you can go into EPLAN as you wish. You can go into AutoCAD as you wish, because next week we have AutoCAD webinar, and you've been told. So you will also see the process, because the bottom line here, do you know the difference between them? What's the difference between these two softwares? There is no difference, because it depends on you using them. So when you come to us, we train you on design, we train you on drafting. So drafting process is you understanding what we call the interface. Do you know the interface? So let's say if I'm doing it on AutoCAD Electrical, I can just use the template for an AutoCAD Electrical, but the design is the same. Does anything change? No. The software is different, but everything that I'm going to design, and just in a few before I finish, this is my last concept and I'm in 11 minutes, I'm actually opening EPLAN and showing you what we do just in a nutshell. But the design process is standard. When you come to us, we show you how to design. We show you how to draft. So if you want to AutoCAD design work, you go on AutoCAD and draw your system. You can actually design an entire system in these cards. But if you don't know where the values are coming from, where the components are coming from, there is nothing much you can do. So it's either you can go with AutoCAD or you can go with EPLAN, but the reticulation is the same. So maybe today I'll show you the strongholds of EPLAN. And then next week, Engineer Okumu will give you the strongholds of AutoCAD. But remember, I am an ex-AutoCAD expert. I know how to use AutoCAD proficiently. But now the reason is we have different environment. Every employer has their requirement. If your employer wants AutoCAD, master AutoCAD. If you have an employer that wants EPLAN, master EPLAN. Either way, you know how to design, drafting isn't an issue. You can use SolidWorks. You can use anything you want, but the bottom line is garbage in, garbage out. You don't do proper design, your drawing are useless, we don't even care about them. So that's just the painful process that we go through in the real industry. We don't really care about fancy designs and drawings and what you come up with. We really care the thought process. And I've actually taken my time. That's why I'm in 13 and I've actually tried, because whatever I've just done is quite extensive, just shortened for you to get the glimpse. For students in the room, nothing is hard. It's just like A, B, C, D. You just put a lot of concern, put a lot of work, just be sensitive on nitty-gritties and do the design. Nothing much. So that's actually the end of my presentation. And just allow me show you just simple AutoCAD work and EPLAN Electric P8 work. And as my software is launching, you can actually ask your questions. Or Engineer James, you can pick up as my software is launching, please.
Oh, all right. Thank you very much, Engineer. That was a very, very comprehensive presentation. Let's celebrate. Let's appreciate Engineer Edgar for the training, and that was excellent. I feel like personally now I have also an idea on how I can be able to size a simple system for my house. Apologies, I'm having a bit of an hiccups, but all is well. So I would want us to go to the Q&A session. In case someone has a question, you can ask, and then engineer is going to respond, please. Thank you.
Any questions? You can just unmute and ask. I think you can also follow on the chat, Engineer James. Maybe some people are asking questions.
Bwana Edgar, if I may just make a comment before you address the questions that will be coming in.
Yes, Ben.
I think what you've shown the engineers in attendance is just what I'm very sure they've not encountered anywhere else, that I can be sure. The reason why I'm sure is because that's what happens behind the scenes. That's what we never actually show, because there's no point to showing it. And because showing it will take a lot of effort and someone might not be really interested in all this. But I want to make a point. The questions that were asked in the comment sections, I tried to address as much as I could earlier on. But there was a question from one of the attendants. Let me just get the name. They really wanted an example to be done just like you've done. You had not reached that section. And that prompted me to at least make a comment.
Okay.
Electrical software, hizi mnasikia AutoCAD electrical, what you hear as AutoCAD electrical or EPLAN or ETAP, all those are not design softwares. Have that clear in your mind. We don't design using the software. We draw and draft. We use these softwares to present our design, but design happens much earlier before all these designs are drawn. So when you come, you don't start from drawing. You can't attend a webinar and expect that we should show you a design you want to do it, because then we will not be showing you anything. What we will show you is how to design. Then drawing, it's just actually like you could sketch with a pen on your paper. That is now what we do with the computers, with the software. So let's have that in mind as engineers, that moving forward, even as we enroll for this process and everything, we are not just getting into a course and starting to draw something. That one will come last, and it will be the least of our efforts, because it is the easiest part of the design criteria and the design process. So engineers, we want to welcome you to all this, and we want to tell you what engineers do is not drawing. What engineers do is design, and what engineers do is what engineer Edgar has shown you in a nutshell. It's quite a process. It takes even a week or a month or years at times due to project issues, but it takes quite a lengthy duration. So be ready to go through it if you want to know, and we welcome you. You will know certainly once you register. Thank you.
Thank you, Engineer Okumu, for that. It's a good feedback, and I think if I came here and started drawing, I'm telling you, I'll be lying. Engineer Okumu is very clear with that, and I like the way you put it. I'm telling you, I'm actually currently with a community, and we do design every Fridays, Mondays, and Sundays. The number in the group is 48, but we always just attend 12. You know why? Because it's not fascinating. These things are not concept you can just wake up and just start doing. I followed your text on WhatsApp on WhatsApp. People say, I want AutoCAD. I'm telling you, only 2 days. It's a discouragement. You can take it of some sort. But the truth is, you know how to design, you know how to draw. And engineer said, drawing is the least of your worries because it's easy and simple. I actually didn't present all of my slide because I think some of them is more on what the sessions will be like. Because if I want now to design the power reticulation, I need to go through EPLAN drafting sequence. I start from single line diagram, I do multi-line diagram, I do control schemes, schematic diagram, I do layouts. So when I come to EPLAN, this sequence is just simple. I need to start with a single line diagram. This is a power reticulation, but for a main distribution board. And this one is going to supply a KTDA system, Kenya T development. This is actually a project for Buhani engineers. It's for Kiptere, okay? So we have systems that needs to be supplied with power, but now you need to size all of them. Now this is an industrial sizing. Whatever I've just given today is residential. But when you come to our programs, we do all the three. We start from residential work, we do the industrial, we go to commercial because the permutations are different. And that design work gives you now the clear clue on how to come up with the drawing. So when I have now this system, I have my main incomers, I have two generators, that's a 640 and we have a 500. And then I have a transformer coming in. So all these are just symbols and lines drawn. And then I go to outgoing systems. I have a breaker going out, and then we have instruments, measuring instruments, and then indicator instruments. And then I go to a specific, maybe office block. I go to withering troughs, wood palleting. So once you now do this single line diagram, any engineer who is describing the system on site, if there are faults, or maybe maintenance going on or downtimes, someone can just go and check on the drawings and maintain a system. So once I do this single line power reticulation, it's easier for me to do it in a single line diagram. But now when I'm in the workshop, the technician in the workshop will not actually use this. Some who are experienced will use this because we come up with a schedule. I have two bus bars for this system. Bus bar 1 is scanning all these loads. Bus bar 2 this, and we have a bus coupler here. We have a bus coupler here. So we have different architectures for SLDs, and they are a lot. And you can do this on AutoCAD as well. Now, once you represent all these, you need to come up with multi-line for someone in the workshop to be able to actually now manufacture the system. So this one is purely now on the real connection. We call it a wiring diagram, or in actually design term for switchboards, we call it single line diagram. So that's the next stage you go into. So you do your single, you do your multi. So if you have controls, let's say if you have a changeover system and you need to develop a control for that changeover, you do that. But again, all multi-lines need to provide a clear connection of all the components that are used sorry, for that system. So that if you're connecting to a specific device, someone will know, I have CTs, they are coming into an energy meter. The energy meter has a communication port. It means you can do a daisy chain to collect what we call data for BMS, building management systems. And then you go further, you remember you have a power factor. So if you go into the multi-line, I have represented my power factor, starting from the main breaker and then to the described capacitor banks. We have the steps plus the capacitor contactor plus the protection breaker. And then I need to come up with what we call the controller, the power factor controller. You need to now develop the system. So this is now what we call drafting. For me, if you've done sketches when we were little, drawing oranges, mangoes, and all that, once you do practice with this, it's like just doing normal drawing. And Engineer Ben puts it very well. You can do all this on just a piece of paper. But what are the concepts here? You need to know symbols, and you need to know to come up with different components. So this is a power project. We have controls. Because now, after I've done these two circuits, single line and multi-line, I can do layout. Now, this is what goes to the workshop. So I have the three SCBs. This is a bus coupler. It is coupling bus that is supplying the bus on the left and the bus on the right. We have generator 2 here. So you know now, this is something that we train you on, but it's a practice you need to do. You just do a lot of practice and you can actually develop any system. So remember all the motors that are supposed to be supplied at KTDA factory. They are just tapping from these breakers. So we have specific concepts we go through when we are studying EPLAN. And I think maybe someone wanted to see me doing this. I wouldn't do this in a session like this for sure. Because this thing takes time. This drawing I did for 6 hours, constant, without like doing anything else. They look like this, simple to understand, but doing them needs a push. And that's why engineer tells you, if you pick the components that you need to understand the software, it's easy. So I tried on the slides to provide all the concepts we do under EPLAN. Engineer will give you on how to go about the AutoCAD. And pick a way. You can actually, if you want switchboards, we can do switchboards on either softwares. So if I come to EPLAN, I need to show you how to create a new project. I show you about project properties, page handling concepts, page types, insertion center, edit tools, connection symbols, navigation concepts, macros, terminals, cables, parts management, device concepts, cross-references, grid and snap tools, types of schematics, 2D panel layout, bills of material, because it's automatically generated nowadays, file types and extensions, basic projects. You can actually customize your templates. Like, let's say, I managed to customize this. This is for Bohani specifically. I can customize for any company I need. And that's the last concept I have here. It's called basic project templates. You come up with forms and plot frames. You can customize as you wish. And then we have the workspace. For people who like white screen, black screen, you can change the workspace to be the way you want. Okay? So at that, it now makes me conclude from a point that if you really want to design, come up with the design consideration processes and then go to drafting. So if you want to run motors, these are actually what we call forward reverse star delta controls. So I have like, these are identical motors. So if you understand one, you go for the next same. So you have main incomer, you have MPCB, you have the 4 contactors for the forward reverse star delta, and you have a motor and terminal block. So you need to create controls for them, but you need to start with a power circuit. So power circuit, everyone knows. You need 4 contactors, one for forward, another one for reverse. And then you need for star delta, star and delta. So once you put together, you take it in a star delta motor, you now come up with a control for the same. So once you've done that, you need a phase failure monitoring relay, you go into the controls, and then you develop the logics. And I have a very easy way to do this, because now that brings me to the last introductory before Engineer James takes over. We have different programs coming up. And I'm telling you, it's fascinating from the start to the end, how to come up with electrical switchboards. Those are panels and designing training. We have electrical power systems design training. We have building monitoring systems and home automation design system. We have classical controls. This one is one I was talking about. You don't use PLCs, you use relays and contactors. And then from there, you graduate into automation system design training. That is PLC. And we also have the embedded systems. It's a program that is on the pipeline. And as James tells you, all this will have a mega lab. We have a lab that is coming up. You just come in for our practicals and you feel like you are, I don't know, in Google or maybe I don't know where. I know you can feel it's an overpromise, maybe to some of you, but we don't joke. It's reality. I've worked with James and I know the type of person he is. So if you're told you need to find a niche and concentrate on none. Pick on anything. We have robotics and intelligent system design trainings coming up. So the one that starts will be actually the August intake for the switchboard. 4 weeks hybrid, 3 days per week, training fee at a very friendly fee. We are not actually going to press on that, but I know the economy changes, things change. But we start from a simple, humble beginning. These programs are from the onset. We haven't done them at Roadsub. And Roadsub has done a lot of research to make sure that they bring the best on the market. So depending with how you wish to go about this, you can convince yourself as many times as you want. But the bottom line is you need to put in effort to get an outcome. And that effort starts with you. And I'm giving you this as a motivation. I've gone up and down. I've actually gone through havoc of life to pick a point of just understanding something and becoming an expert in it. I'm only 5 years out. Some people in this group, they are almost 10 to 20. It means you have a lot of expertise. You only need someone to direct that expertise, and you now find a proper configuration or a convergent point for your life. So I'm actually finishing this session, and I think we will have a lot. And in case you have any communication with us, our numbers are there. Text us, talk to us. We can actually talk a lot. I don't have more to say, but to take the program back to Engineer James. Thank you guys for coming. Thank you for listening.
Excellent. Thank you very much, Engineer. That was an excellent session altogether. Thank you, Engineer Ben, also for answering and responding to the questions of our amazing engineers. And therefore, please, we can call it a day at that point. We'll have our second webinar the following Saturday, and this will be on AutoCAD drafting. So we'll see how we can build up on this class so that then we can proceed at least to draft some of the things that we've learned here. So apologies again for my hiccups. It's crazy. Have a good night. We'll share the recording. You can be able to access it directly on YouTube. So don't worry. Once it's ready, I'll be able to share. Good night and wishing you a fantastic time. Good night, everyone. And thank you so much. Good night.
Good night.
Engineer James, have you stopped the video?
Yes, I'm doing that shortly. Thanks.
I've just shared the link to the WhatsApp. There are people asking if they can be added and such. I've shared the link to the not WhatsApp, the link to that WhatsApp group in the chat box in the chat, so you can.
Have you shared it here?
Follow.
Hi.
Hello.
Engineer James. This is Chief
Yes,
Talks
please.
Investments. This is Engineer Chitai. I am with my colleagues, my team. I wish to know if the all forthcoming training sessions will be payment plan proof or will be free, so that I can budget myself for them as well. Kindly.
Thank you. We would have wanted to do these trainings for free. But again, as he said, we have to pay for a lot of resources. And therefore, we have agreed that the programs will be only at 12,000, just like we do with the other civil engineering programs. Thank you.
I wish just to bargain right now, since I'm paying for almost 30 people. Kindly, 12,000 is too much. And as electrical engineers, we wish just to say, we can't say it for free, but sir, again, I can't train them by myself. Please, if you can do it at a subsidized price, bei ya mwananchi, bei ya Kasongo. Mimi ni Mkenya, bei ya watu tuko hapa kwa sababu ya kufanya Kenya become great again. Why? Because engineers are what make things become beautiful, are what make sophisticated designs look more easy. And we are here. I do solar, I do everything. But personally, I'm requesting, if from the 12,000 fee you can make it up to hii inaweza kaa mbaya, inaweza kaa matusi, lakini kwa unaweza fanya 2,000 inaweza kuwa poa.
Thank you. I've heard you, so I'll make a decision on that. Thank you. Thank you, everyone. Good night. Take care of yourselves. Let's keep talking. Thank you very much.
Okay, thank you. Thank you very much as well.
Karibu Owen. Thank you for participating.
So mmesema training inaanza August eh?
Yeah, the first cohort is in August, but in case of any changes, the engineer James will confirm with you in case of any changes. But the first cohort, because we need to have 2 webinars, and then we also have a boot camp that is coming up. I don't know, Engineer James forgot to talk about it, but we have a boot camp, I think, on 7th. We have a boot camp on 7th next month for all university students, technicians. So it's also online, and it covers all the Autodesk softwares, I'm sure, EPLAN included, plus AutoCAD and the rest. So for electrical guys, you've got covered because I and Engineer Okumo will actually make sure that you receive everything you need.
So na hii ya August itakuwa physical ama watu tuko mbali tunaweza fanya vipi?
Hybrid, it's hybrid, but since it's design work, online itapewa kipaumbele because design work, you don't need to travel. Once maybe we've talked about coming up with a space for practicals. Once it's completed, to incorporate the practice. But for now, the value that we're giving for this training is just because it's going to be an online program. That's why it's 12,000 actually. So if you get now to the point where we need to do the labs, and that's why we are telling you we are getting in more resources to actually make sure that you gain all, so that we ukitravel ukikuja huku you have a reason as to why you're coming. But for now, most of it, Shadrach, will be online.
Oh, true. Okay, thank you.
Karibu sana.
Sorry, I also had a question. The AutoCAD session, will it be paid, Ama?
For the webinar, or actually
Yes,
we have
yes, the webinar that
no,
will come
it's
next
free.
week.
The webinar is free. When the webinar is free.
Okay.
Yes.
So I think sorry, I think maybe if from now going forward we need
Yes.
to know the sessions that will be charged, and also
Okay.
the workshop if it will be charged, so that we
Okay.
can also plan ahead.
Sawa. So I think whatever Engineer James is actually doing, we've talked about incorporation of electrical trainings just coming up. So we are coming up with proper structures to also benefit you guys. I know Mwananchi and all those, and also peer planning for your finances. So we always come up with a conclusive timetable of all the programs within a year that will be done. So Engineer James updates that in our website. So you can actually visit our website. The link will be shared to you guys so that you can see. So we'll make sure for your planning, we do it as early as possible.
Okay, thank you very much.
Karibu.
Hi, once again, just to
Hi,
confirm,
E-Tracks, yeah?
yeah, from Engineer Society Trucks Investment. Kindly, so that will be like a class session, a period of maybe 4 weeks, 3 weeks, or am I wrong?
Why do you
For the
call it
12,000
crash? Why do we call it crash? I think for
class?
the
No, class, not crash. Class.
class.
Like this is AutoCAD Inception for someone who has a laptop with an AutoCAD with an E-plan for
Okay.
electrical engineers to know how to use it. So to speak, is from maybe some of us or some of them are
Yeah.
from the craft certificate, they're from the diplomas that maybe, or institutions that
Actually, yeah,
didn't have such facilities while we are doing our PhDs or our degrees,
okay,
whereby we could have time with our lecturers giving us all these and testing us. It is also a good platform for such guys or such of my team to
okay,
know and to understand and to
yes,
see where we can key in or fit in, but it
okay,
is for the benefit of the name of electrical engineers. It is
okay,
for the benefit of the modern development, the smart home systems, the instrumentation, the smart instrumentation, whereby
okay,
we can get to configure things using our computers, where we can get to know before I go to a client, I can
yes,
open this app and here, and I know this is happening, this is happening. I've done that severally, but
okay,
as I said, I can't teach all of them. But I
okay,
believe in this sharing, we can help each other to know
yeah,
and to become great than any other
okay,
technician, than any fundi wa stima. Let's just, so to speak, the name that is outside here. You see,
yeah,
kindly
I
just
get.
look into it in that direction. Kindly.
I get you. I get you. Actually, I feel your sentiments, but all the time, remember, knowledge is something that is dependent on what you interpret. If you actually tie money to be a reason of constraint, automatically it will be different. But also we have negotiations, which is prudently enough an economical issue that can always be discussed. And I've actually followed your conversation with the engineer James, and he's a very diligent man. He'll actually give you an offer hata wewe mwenyewe utashanga. Sometimes we consider growth from a point of putting into constant all the other factors. I know my level of academic haezi kuwa like the others, but I'm a damn good.
We appreciate.
I'm actually a person who trains those people who watu wenye wanafeel ni kama hawezi elewa. Mimi naweza
I know
kwambia
you.
all
We've
craft.
met.
Yeah, actually, I know all craft people, they actually have one thing that I always admire, the practical aspect. And I will tell you, Chitai, for free. When we started this, we started from that practice. Before you can even sit behind a computer and do any design work, someone actually, when you started, wendo ulikuwa ule mse wa mkono, the way you put it. But these guys, they also have a chance, the same like you, same way approach. But kumbuka, wewe vile unajituma, you can only be a motivation to someone else. Ndo pia yeye ajitume vile wewe unajituma. Because
I
I know
agree.
what you can do, but someone else admires what you can do, and they actually want to follow that footsteps. But it only takes those people who are courage to come na kwambe, oya, engineer Chitai maze, me actually naomba tu niokole. But people don't do that because they feel ashamed. Someone maybe looks at you na anakuenvy. So the envy could be a propulsion or a repulsion for that person who actually needs to know. Mimi engineering nikuje kwako nikuambie, oya, niko na hii na hii maze, can you help me? Wacha tu nijireduce nijue tu sielewi. So when we come to these kinds of program, we will make sure all the permutations we put into consideration is to push for all of us to have the inclusivity. And that's actually the slogan we want. Even ule mtu amefanya certificate, craft, all those things, they can actually buy a computer one day na watajua guy, mi sijai work na comp for the rest of my life, but leo nimejipata nimeshika comp. You come to our, I don't know if you come at Westlands where Nini Road Sub is. You need to visit us. So you see whatever setup we have. We have computers there. You actually just come and sit there. You don't need to come with your computer or something. But if we reach out,
Welcome.
it will be easier, and you can also understand. You can bring your 30 guys and we will find a space and train them. Unatupatia tu maybe 4 hours of your time. I know you guys are busy people. And then you can actually gain some few insights. You know what we call customized trainings. We have customized trainings, and those can be subsidized when actually Engineer James gives you that feedback so that we know how to approach. We will help each other and we will grow. Now,
Thank you so much.
karibu bro.
Naweza request kitu moja tafadhali?
Yes, so on.
Yes, please. I just had something to say. Kulingana na group, I would
Yes.
request if people don't be aggressive and
Wallahi,
because this is a learning platform
wallahi.
where
I've seen
we're here to learn, where we are here to grow. And please, because at the moment right now, the group is closed to admins only. And where there's someone who maybe has something that he can share and help others in this industry of ours. Because as per Engineer Edgar, this is a broad industry
true.
where we need to grow. You may specify in one category, and there are people who need to specify in a broader,
Yes.
uh, let's say, field. So I
Yeah.
would request let's not make this group,
Bro,
the WhatsApp
si
group
utakutana na
specifically.
nani?
Let's not make it something where you're coming to advertise your business, where you're coming to speak things that do not concern the group.
True.
Let's stick to what is major here. Let's stick to growth. Let's stick to our industry, and let's talk about things that will help us grow as engineers and
Thanks.
technologists.
Thanks.
That's all I have.
Thanks for that. Actually, as I said, I followed most of your chats. People, you're just a grown up. You know what's good, you know what's bad. You don't need to target anyone because of what they know or what they do. You can just pass your sentiments very calmly with discipline, and it actually goes a long way to another person. If I make a mistake and I tell Owen I'm sorry, it's something that it goes a long way. But now to start making it to be like something big, or maybe you go off board, it's not fair. I know we are humans, but again, Owen is clear. What is the common goal? We came here to learn from each other. It's not to target anyone. So we can actually be maintain that, and it will help. We don't need like to say now we need another group for people, because everyone has their own behaviors. You can't change anyone. But as we said, you know what's good, you know what's bad. Just do the right thing at the right time. We are not interested with your personal life. We are not interested with maybe things you know or you don't know. But if you're helping someone, then we are interested. So you can take someone from point A to point B just diligently. People are smart out here. And someone said kwa group, huwezi jua unakutana na nani. The next day I go to a job, I get Owen. I get the job because maybe I was good to him. Or maybe it's not even about the interview atanipea. Itakuwa tu like mtu anakuona you are actually a person who is respective. Just be respective all the time. Okay?
Hey guys, let's go and sleep now, guys. It's already it's almost 11, please. Thank you.
Mi hadi nasoma chats.
Che.
Ziko interesting though. Actually,
Yeah.
I'm just because I'm reading the charts. People are actually smart out here. People are smart. People are smart.
Yes. Please, let's do so because of the next session.
Angusha,
We are coming about AutoCAD.
yeah.
Let's just make it civil. Let's make it human. Let's make it a platform for growth, a platform for people to grow. Let's just make it that.
Nice one, Owen. So mi nishamaliza hizo text zenu. So in case of any question, you can reach out. Good night, guys. See you. Jamo, si baadaye.
Baadaye, bro. Thanks.